This video, we're going to do a last example of a Lewis structure where we might need to use formal charges to find the preferred structure. Before we do that, though, I just want to mention I did forget one of the resonance structures for sulfate. And I'm just going to draw it over here, and hopefully you maybe figured it out yourself. I forgot to put the one where the arrangement was like this. So the double bonds there and the single bonds here. I think that was the one I forgot. Yes. Like this, this, these lone pairs here, and then our little charge there. Like that. All right, let's go try this one out over here, H2SO4. Now, typically when you have acids, what you want to do is you mostly want to connect your atoms to the central atom. Now, this is the molecule, so the hydrogens are still connected to the to each other, to the other atoms. If you do see a molecule like this, a good practice is to connect all your O's to a central atom and then connect your H's to your O's. That's typically how you should proceed. So we'll start doing that. We're going to do S. Let's leave some room on top so we can actually put lone pairs if we need to. So we'll put S over here. We'll put the O's over here, like this, with single bonds first. And then we'll connect the O's to H's. It doesn't really matter which O's we put the H's on, as long as we put the H on the O's. Now, each O will be able to accommodate one H because the O is already connected to a sulfur. So we'll go ahead and do that. We'll connect this one over here like that, and then connect this one over here like that. We could have done the one on the other side as well, but that's okay if we did this like this. Let's go ahead and calculate our valence electron. So we had 2 from the hydrogen, 6 from the sulfur, and then 4 times 6, 24 from the oxygen, which is 32 total. And we've connected everything here with single bonds. We have 1, 2, 3, 4, 5, 6 single bonds. So it's 12. And so it leaves us with 20 electrons left to place. And we can go place them around our peripheral atoms first. So we'll do 1, 2, 3, 4, 5, 6. That leaves us 14 because that one's happy. 1, 2, 3, 4, 5, 6. That leaves us with 8. Now, we wouldn't place any around hydrogen because they're already happy. But let's go place some around the oxygens here because we need 4 on each, right? So 1, 2, 3, 4. 1, 2, 3, 4. And that gives us 0 left to place. And it looks like all our oxygens are happy and all our hydrogens are happy. And if you look at it carefully, our sulfur is also happy because it has 8 valence electrons. But don't forget that sulfur can often take an expanded octet. So let's go and see if an expanded octet structure might work more effectively. And all we have to do is really draw it out to see if that's the case, if it will work, and figure out what the formal charges are. So we can turn the oxygen over here into a double bond and get a structure like this. So that's one possibility. We could also do it twice. We could turn this one to a double bond as well and get this. Now, the thing is here, we couldn't turn the other oxygens, we couldn't give them double bonds because they already have 2 lines connected to them. A good rule of thumb is that if you have 2 lines connected to your oxygens already, it's usually in pretty good shape and you can't do anything else to it because it can only take a maximum of 2 bonds, and then the rest will be lone pairs. Hydrogen will be 1 line, and then oxygen is typically 2 lines. But we need to choose which structure here is the best structure because they're all technically okay. They're not breaking any rules. One of them is a stable octet. One of them is expanded with 10 electrons, and one of them is expanded with 12 electrons. And so sulfur is allowed to have that expansion. let's go and calculate some formal charges for our different structures and see which one ends up being the best. So we'll start with structure number 1. We'll start with our hydrogens. And so number of valence electrons, 1, minus number of dots, 0, minus number of lines, 1. So 0 for our formal charge for hydrogen. And this is going to be the same thing, 0 over here as well. And to get things done quickly, when you see that there's atoms that are connected in similar ways in different structures, just go and mark them as 0. You just have to do it once. So this is 0 here, 0 here, 0 here, 0 here, because they're connected in the exact same way. Let's go and do the formal charge for the oxygen that's over here. So for the oxygen that's there, you have 6 valence electrons minus 4 dots minus 2 lines. That's 0. And so this is connected in much the same way. This is 0 as well. And this is connected in much the same way. This is 0. This is connected in the same way. 0. This is connected in the same way. 0. This is connected in the same way. 0. So far, there doesn't seem to be much of a difference between these structures in terms of formal charges. Let's take a look, though, now at the oxygens at the extremities. Let's start with this one. So we have 6 valence electrons minus 6 dots minus 1 line. That's -1. And this looks like it's the same sort of setup, so -1 as well. And then any other setups, this is also -1. And we don't seem to have it set up there anywhere else. So -1, -1. Okay. Now let's go and take a look at the sulfur here. So sulfur is 6 minus no dots minus 4 lines. That's +2. So +2, -1, -1, 0 overall. But still, we have quite a few non-zero charges. Like this is a pretty big non-zero charge over here. Let's go take a look at this situation over here. We have, in this case, 6 minus 4 dots minus 2 lines, 0. Okay, so that's good. We have fewer non-zero charges. Let's just take a look at our sulfur here. So 6 minus 5 lines plus 1. So we really only have the -1 and the +1 as non-zero charges here, as non-zero formal charges. Whereas here we have the -1, the -1 here, and then the +2 here. So we have more formal charges in structure 1. So likely this will not be the one we're going to be using. So now we're really deciding between structure 2 and structure 3. So let's go calculate the final formal charges here and here. They'll be the same because they're bonded the exact same way. 6 minus 4 dots minus 2 lines, that's 0. And then this would be 0 as well. And then for sulfur, we have 6 valence electrons minus 6 lines gives us 0. So this structure here has 0 formal charges. There's no non-zero charges anywhere. That's actually the better structure. So therefore, structure 3 is the best structure. Oftentimes, not always, in situations where you have an expanded octet in the middle, it's actually better to have most of your oxygens with double bonds on them, because that actually reduces our formal charge as much as possible. It makes it less negative since you're putting those electrons that were lone pairs into bonds rather than solely on the oxygen. And then it makes the one in the middle a little bit more negative compared to positive, since you're giving it some more electrons to share. So if you can have an expanded octet, it's nice to have oxygen with double bonds where you can have them. And oftentimes when you have charged substances, you'll see some oxygens have single bonds and then some have double. So like we saw in the case of sulfate, you'll notice that we had 2 double bonds here, but then also 2 single bonds, and that kind of matches the -2 that's over here. So the single bonds that we have here, they contribute to the formal charge, -1 and -1, which can translate into that -2 charge that we see up here. It doesn't necessarily cause it, but it's a nice connection that you can make between them. And you gain experience doing that, but this is a great example to do because it's not always apparent how to make these type of Lewis structures. So when you see some like this that look like these acids over here, you want to connect all the oxygens to the central atom and then connect your H's, if you can, to the oxygens and then proceed from there. So that was the Lewis structure for H2SO4. And you can try other examples to see if you can find the best structure for them.